So today we're talking about rotational dynamics, like what happens when an object is under the effect of a net unbalanced torque. Up until this point we've had balanced torques. Now let's talk about what happens when the torques are not balanced. The short answer is it's going to rotate and speed up as it rotates. It's going to have an acceleration. Now if we go way back in the Wayback Machine to the very beginning of the year, we should recognize Newton's second law for things moving in lines. The acceleration linearly is equal to the net force over the mass. Well, there's a very similar relationship for things that are rotating. So Newton's second law for rotation, well, instead of A, we would use alpha for angular acceleration. Instead of the force, it's the torque. Torque is what causes things to rotate. The thing that's a little bit different is the term on bottom. Instead of mass, we have this term I, which stands for moment of inertia. And you can think about moment of inertia as being the rotational equivalent of mass. And so that's going to depend on two things. Number one, how heavy is the thing? Heavier things are still more difficult to rotate than lighter things. And then two, how is that mass distributed, i.e. the shape of the object? And so the best way to illustrate this and understand it is just to pick up some things and make them rotate. So we're going to start off with something simple, like a meter stick. And I've labeled here the approximate location of the center of mass of the meter stick. Remember, to find the center of mass of something, you simply hold it with two outstretched hands like this on your fingertips. Bring your fingers together and they will meet at the center of mass. And that's about the position where you can balance it. Here, after a while, we should be able to explain why heavier things are easier to balance than lighter things. Meter sticks are kind of hard to balance because they're so light. So when we take something like this and we grab it in the center, which in this case is the center of mass, like this, grab it with a single hand and rotate it, this is like really easy. You can do this all day long. If, however, you grab it at the end to where more mass is over this way, no mass is over here, now it's a little bit more difficult. I mean, I can still do it because I'm swollen and stuff, but yeah. But this is a little bit more challenging. Like I can only do this for probably like 12 hours before I would have to stop. Whereas this, you can do that all day. And so you should do this with something that you have around your house. Ideally something that's long. A broom works really well for this demonstration, especially if you can take the broomy part off and get just the stick. But any kind of stick will work for this. Grab in the center, rotate it. Feel how easy breezy that is. Grab at the edge. A little more challenging. The longer the object is, the more difficult it will be to turn it as well. And so it's not only how much it weighs, it's not only the mass, it's also how the mass is distributed. Basically, the farther away from the center of mass your mass is located, the more inertia that thing is going to have. Let's do it with an asymmetric object, like this one. This is a big old rowing oar for back when we used to like race the other school in cardboard boat racing at the Aquatic Center. I've labeled the center mass of this thing, and again, you can put your hands together and they'll meet at the center of mass, kind of like that. Not quite. So if you grab an oar at the center of mass and you turn it, it's a little bit heavier than the meter stick. It's a little bit longer, and so it's more difficult to turn. If I move my hand to the lengthwise center of it, now it's like really difficult to turn. I can't turn this very fast at all. If I were to grab this end of it, besides hitting the ceiling, it's also really hard to turn. If I grab the other end though, not so bad. It's a little awkward to hold, but grabbing it here is actually easier than grabbing it here. When I grab it here, there's a lot of mass a long way from where I'm grabbing it. And so there's a lot of mass far away from the pivot point. That's very difficult to turn. Whereas a lot of mass close to the pivot point, not too bad. I can do this left-handed. So in order to get an appreciation for moment of inertia, try to find some things around your house that are kind of stick-shaped like this. Brooms and mops, baseball bats, softball bats, golf clubs, tennis rackets, although those are usually engineered to be like really light. They all work very well. Grab it in the middle. grab it in the middle, turn it, grab it at center of mass and turn it, grab it at one end and turn it, and you will feel the difference in the moments of inertia when you grab it and try to rotate it at different places. So here, the mass is relatively evenly distributed, both sides. Here, there's a lot of mass far away from the pivot point. I grab it here, there's a lot of mass, but it's relatively close to the pivot point. So play around with that and experience moment of inertia for yourself. Okay, so I've got another moment of inertia demonstration that's a little bit more precise, and it's something we can see and measure, whereas moving like an oar or meter stick is something that we would more like kind of feel. So what this device is basically a bunch of wheels of different radii, which are connected to these 4 poles, and those poles extend outwards, and then these masses that are on the poles can be adjusted. And so here in a minute, I can take this and I can slide it out, and I can do the same thing with the weights on all 4 of the poles. And then around the center wheel, if you will, I've got a string wound around it. And then I've got a paper clip attached to that. And to that paper clip, I'm going to attach a 100-gram mass. Since there is no other force resisting this, this will cause it to fall, and as it falls, speed up. So basically, this is another variation on the Atwood's machine. And we should be able to see the difference in the acceleration when I have it like this and the masses are close to the center like they are now, and when they're far from the center, like in the second demonstration. But I'm also going to go ahead and grab the timer and time it. And again, I'm going to let it go all the way down to the floor so we can really see the acceleration. And the acceleration, you'll notice, is just the angular acceleration of the little spokes sticking out. So let me grab the iPad real quick. So in 3, 2, 1, go. So that took about 15.5 seconds to reach the floor. That's with those masses close to the middle. So we're going to rewind this thing back the other direction so that everything else is the same, and then repeat that with the masses moved further out. Okay, so when the masses were close to the center of the system, like close to the center of the wheel is there, it took 14.5 seconds for that 100-gram mass to fall, accelerate, and hit the floor. Now let's see what that time looks like with the mass of the system redistributed to be further from the pivot, which is the axle right here. And so the mass is further out. The mass hasn't changed. It's just been redistributed so that it's further away from the pivot. So 3, 2, 1, go. Okay, so that time it took about twice as long for it to fall and reach the floor, 30.1 seconds as opposed to 14.5 seconds. So with the mass distributed further from the pivot, this thing is now more difficult to turn. And if you were here right now with me, you could physically turn it, like to rewind this thing, you kind of give it a push and the mass fell off. But it's physically more difficult to push. You can feel that it's more difficult to push with the mass distributed way out here as opposed to closer in here. So the mass of the system didn't change, but its moment of inertia did change. If I were to pick this up and carry it back to the storeroom, it would take the same amount of force to lift it regardless of where those masses are. It's the rotational inertia that increases by moving the mass further from the point of rotation.